Hi everyone. What we're going to be talking about today, we're going to be looking at areas and arc length in polar coordinates. Now, one of the items that we're going to need to recall is going to be from trigonometry. And you see here on screen that I have that recall from trig. And what I want you all to recall is this formula here for the area of a sector. Now, back in trig, we were able to derive this formula of the area of a sector as soon as we had a given radii, a given radius and a given angle theta. As soon as we had a given angle theta and radius, we were then able to find the area of that sector, and that area of the sector was 1/2 radius squared times the angle theta. We're going to use that to build more, or to build this concept of using calculus to find these areas of sectors. Because once again, we're converting all of these grids into polar coordinates, so that means we're going to be able to use the polar coordinate version of this areas, which is given here, to be able to determine what is that area. So let's say that we had some function in polar coordinates. Alright, so what I'm going to do here is I'm just going to draw some function in these polar coordinates. Alright, it'll look like this. And this function, I'm going to say this is r is equal to f of theta. And what r is basically saying, or what the radii is basically saying, it's saying that at the from the pole on that polar axis, it's going to extend to this point here, and then after that, once it starts traversing through all of those angles, it's going to start creating this specific curve here as it's traversing from the angle, as it's traversing angles theta. Alright, now once we have this, then we're going to say, okay, well, we want to find a certain area. So what I'm going to do is I'm going to create two different bounds here. I'm going to create one of these bounds to be one of my angle measurements. Let's go here. Alright, and then I'm going to create another bound to be another one of my angle measurements. Let's see here. There we are. Alright, so these two segments here, one of them is going to be angle 1, which we're just going to call A. The other one's going to be angle 2, which we're just going to call B. And the region that we're concerned with is going to be the region right smack in the middle here. Alright, so this is the area that we are focused on here. And this area, as you can see, is then bounded by this function and these two angle measurements here, theta 1 and theta 2, which again we're calling just A and B. And what we then want to do is we then want to figure out how can we calculate this specific area. Well, one of the things that we can do is we can start identifying smaller sectors. Alright, the same thing that we've done from the beginning of calculus, once we started getting into the Riemann sum, is that we want to keep taking all of these smaller and smaller pieces, that way we can sum up a total of a whole. So, let's go ahead and let's start breaking this region into smaller sectors. Alright, so what I've done here is I've then subdivided that region into smaller regions or smaller sectors so that we'll be able to then calculate them. Now, typically we work with delta x in calculus, right, back in Calc 1 and the beginning of Calc 2. However, in this particular case, we don't exactly have that luxury to be looking at delta x, because this graph, even though it's plotted on the x and y coordinate system, it's going to exist in polar coordinate form, which means we're not going to have these delta x values that we're going to be observing directly. Instead, what we're going to have is we're going to have a difference in between these angle measurements. In other words, we're going to have these delta thetas, or this change in theta that we're going to be observing. All right, so those change in thetas are going to be the ones that we're going to have to be looking for. Let's go here, and let's go here. There. All right, I think that should be enough. These here, oops, are your delta thetas. As such. All right, so instead of delta x, we have this delta theta that we have to then consider. All right, we're going to be looking at what is that change in theta for this overall region that we're observing. All right, so once we start looking at this, then we're going to say, okay, well, now let's see how we can start building this specific area. Well, what I want to do is I want to pick a specific point or a specific angle within this sector, or within one of these sectors, and I want to go ahead and analyze that sector for that area. So what I'm going to do here really quick is I'm going to pick some random point here, and again, maybe not so random here, but we'll go ahead and we'll portray it that way. All right, now this value that I'm choosing here, this blue line that I'm looking at here, I'm going to call this theta I, and this is going to be a sample point that I'm going to be looking at. Now, what does this point actually represent? Well, this value right here is just going to be the function evaluated at that given theta measurement. So if I want to then find the area of that one small sector right in here, then that means I'm going to be able to use this specific area. So I'm going to go through and I'm going to make some adjustments here. All right, the adjustments that I'm going to make is that this interval here in which the sample point lies in, this is going to be theta, whoops, this is going to be theta of I minus 1, and this is just going to be theta of I. And again, this is just a sample point within that interval. All right, so in order for me to then try to approximate that area, and I'm going to highlight that area in, let's say, a light blue here. And that's that area right in there. So if we're trying to calculate that area of that sector, then we're going to say, okay, well, that area of the sector that's going to contain that sample point is then just going to be the formula 1/2 times the radius, but the radius is that function evaluated, oops, let's write that better. That's going to be the function evaluated at the sample point that we have chosen. So that's my radius. And theta, well, theta, that's just going to be my angle that is being traversed here, that change in theta. All right, but again, that's only for one sector, and it only gives an approximation to it. Well, what if we don't want an approximation? What if we want an actual count for, let's say, the total area, or a better approximation for the total area that's highlighted in yellow here? Because again, this is only one of them. So what we do then is to approximate the area for that region, we then take the summation of all of these indices, of all of these individual areas that we are observing here, and we just sum them all up. So that's going to be 1/2 multiplied by the radius of each individual sample point that we're looking at squared multiplied by delta theta. This should give us a very good approximation for this specific area in yellow. Alright, but again, we're not in the business of getting approximations at this point in time. We want actually firm counts, firm values. So what I'm going to do then is I'm not going to approximate it using n subintervals. Instead, what I'm going to do is I'm going to get a good approximation or a very good value by taking an infinite amount of these subdivisions. So I'm going to take the limit here as summation goes from 1 to n, and this is going to be for 1/2 multiplied by the radii that we're looking at for each individual sample point, and then multiplied by delta theta. Well, this here kind of looks like that Riemann sum. That's the Riemann sum, which is really good for us because knowing the Riemann sum back from Calc 1, this now allows us to say, hey, this can be interpreted as an integral. Well, what is that integral? The integral is moving from, the integral is going to be calculating the change in the angle measurements. Therefore, the angle bounds are going to be from A to B, or we can write it theta 1 to theta 2. The function that we're integrating is this 1/2 multiplied by function of theta, in other words, that radii function that we're observing, multiplied by delta theta, in other words, the change in theta. Now, typically, we like to write this as the integral from A to B, and this is just going to be 1/2, whoops, what's going on here? And this is going to be 1/2 r squared, and this is going to be d theta. So this is what we're observing here, and this is what we're going to be using when we're talking about finding areas within these polar coordinate graphs. Now, I want to take a few minutes and I want to show you more of a graphical representation on GeoGebra. That way we can go ahead and we can start talking about areas between different radii functions that we're going to be coming across. So follow me along to GeoGebra really quick. Alright, so here we are on GeoGebra, and what I've done here is I've created two different graphs. One of the graphs is this graph in blue, the other graph is this graph in purple. And what I'm going to do at this point in time is I'm going to start traversing the angle measurements, and I want to look at what area is encapsulated by the inner radius of the blue graph, but the outer radius of the purple graph. So notice we have this area being traversed here, or being sketched out, right? All of these line segments here represent those radii measurements. And essentially what we're doing is we're taking all of these radii line segments and we're adding them up. Now in this particular example, right, we have two different radii functions. Well, those examples we might actually be coming across when we're doing this within our calculations, and we will see them in a little bit. One of the other things that I want you to focus on are these intersections. Will it be possible to find those intersections, right? Well, let's see. What I want to do here is I'm going to convert this grid into polar form. Here we are. So there we are. Now we're looking at it in polar form. Looking at this in polar form, we can then see, hey, we do have intersections, and they are going to be at those very specific theta values. Which means back into our formulas that we found, all we then need to do is integrate what are we increasing from one angle to the other? Where is our starting angle and where is our stopping angle? Notice, if I traverse from this angle over to this angle, it doesn't get me what I need. So, we must be able to go back into trig and to see which angles are coterminal angles. Because if they're coterminal, then that means we're going to be able to interpret them slightly different or put them back into the domain that we need to integrate. So, let's go back onto GeoGebra. Sorry, let's go back on, got caught off mid-sentence there. Let's go back to the class. All right, here we are. So an alternate formula, what we were just talking about, we can be looking at the area between two different curves where we have f of theta in one radii, and we're going to be subtracting it by a different radii function, and this is d theta. Now this can be condensed because, again, the limits of integration for each integral and the differentials are both with respect to theta and they have the same limits of integration. This can look like 1/2 the integral from a to b, and this is going to be for f of theta squared minus g of theta squared, and this is all d theta. Alright, so again, this is going to be when we have a difference in between these two curves. So we just have to make sure that we're open to that idea when we're looking at the difference between these two curves. Alright, so let's go ahead and let's start our first example. So here goes our first example. Sketch the curve. So I want you to sketch the curve and find the area that is enclosed by the cardioid with equation r is equal to 2 times 1 plus cosine of theta. There we are. So we have to then go through and we have to sketch this curve. Now what I want you to do is I want you to get a really good sketch of this curve. That way we can start using that sketch. Alright, so take some time, sketch it out, and I'm going to go through and I'm going to sketch this out on GeoGebra, and then I'm going to import that picture onto here. Alright, so again, put pause on the video, sketch this curve, and we'll keep going in just a little bit. Alright, so here's the graph of that cardioid with equation r is equal to 2 times 1 plus cosine of theta. Now, the traversing that is taking place so the traversing is moving in this direction. There we are. So it's moving in this direction. Now, where does it start? Well, we have to figure out where the angle measurements are going to start, right? Are they going to go from 0 to 2 theta? Are they going from 0 to pi halves? What is it traversing through? Now, if you notice as you started graphing this, we're going to start at the angle measurement for theta is equal to 0. And as it keeps traversing, once it gets over to, let's say, pi halves, at pi halves it's going to be at 2, right? Because that means cosine is going to be 0. And when it goes to pi, it's going to go, condense back down to the pole. Once it does that, it's going to keep going all the way to 3 pi halves. It's going to be at -2. Or sorry, it's going to be at 2, radii 2, and then after that it's going to keep traversing all the way to 2 pi, so theta here is also going to be 2 pi. All right. So as we start looking at this now, we can then start saying, okay, well, we have to try to find the area inside of this cardioid. So working with the area formula, we can now see it's going between 0 to 2 pi. And since we don't have a different function that we're trying to find the area between, what we're going to do is we're just going to say this is going to be 1/2 multiplied by r squared, and this is going to be d theta. Now, what is the r squared? Well, the r squared, that's just going to be the r value, or the radius that we're observing. So 0 to 2 pi, and this is going to be 1/2 multiplied by 2 times 1 plus cosine of theta. That's going to be squared, and this is d theta. All right, let's go through and let's simplify then. 2 squared, that's going to be 4, so 4 divided by 2, that's going to leave us with 2. So this is really just 2 times the integral from 0 to 2 pi. And I'm going to expand this. All right, that's going to be 1 plus 2 cosine of theta plus cosine squared theta d theta. All right, so that's what we're looking at here. Now, what I'm going to do here as well is I'm going to go ahead and I'm going to make a substitution here. The substitution that I'm going to be making is for my integral for cosine squared. So we're going to go with cosine squared theta. We need a power reduction. That power reduction for cosine theta should be 1/2 multiplied by 1 plus cosine of 2 theta. And making this power reduction should help us evaluate this integral slightly easier. Oops, excuse me there. 1 plus 2 cosine theta plus, we're going to make this substitution. So that substitution is 1/2 times 1 plus cosine of 2 theta. And that's all d theta. All right, it's looking pretty good so far. Now, I do have a fraction here, so what I'm going to do is I'm actually going to take this 2 that I initially factored out of the integral, and I'm going to distribute it back in. That way it cancels out with this half. I don't like to integrate with fractions too much. If I can avoid it, then I will take that approach. So I'm going to distribute that 2 back in. So 2 times 1 is 2. 2 times 2, that's going to be 4 cosine of theta. 2 times 1/2, that's just going to be 1. So then this just frees it up to just be 1 plus cosine of 2 theta. And this is all d theta. All right, looking good. And let's combine some like terms here. 0 to 2 pi. This is now going to be 3 plus 4 cosine of theta plus cosine of 2 theta. And this is all d theta. Man, this is looking real nice. So what we're going to do now is we're just going to go through our integration techniques. So we're going to integrate 3 with respect to theta. Well, 3 with respect to theta, that's just going to be 3 theta. We're going to integrate 4 cosine of theta. The antiderivative for 4 cosine of theta is just going to be 4 sine of theta. And then we need an antiderivative for cosine of 2 theta. That's going to be 1/2 multiplied by sine of 2 theta. And we're going to evaluate this from 0 to 2 pi. So now we can go through the evaluation, but I feel very confident that you guys will know how to do the evaluation, so I'm going to leave that up to you. All right, so the evaluation is up to you. I want you to keep going, so feel free to put pause on this video and do that calculation really quickly. The answer should be 6 pi. Now, what does that mean for us? That means that the area right in here that we were initially looking at inside of this cardioid, that area will be 6 pi. All right, looking pretty good. Now, that's an example where we have this specific area being given to us, or sorry, where we have to find this specific area. Well, what if we have to find an area that's going to be bounded by two specific curves? Can we then do that? That's going to be this next example. All right, so here goes the next example. All right, so here's the example that we're going to be looking at. We want to find the area of the region that lies inside of the circle r is equal to 1 and outside the cardioid r is equal to 1 minus cosine theta. Now, I want you to spend a little bit of time to try to see if you can graph these two polar functions on the same polar grid. All right, so take some time, go ahead and do that. If you need to, go ahead and put pause on the video. I've already taken the liberty of graphing them, so I will be posting that graph here, and that graph again is an export from GeoGebra. So if you haven't done so, go ahead, take some time and go ahead and graph it yourself. So put pause on the video, go ahead and do it. Now, if you're watching on screen, I went ahead and I imported the graph here. And I want to go ahead and I want to find this specific area right in here. So this is the area that is going to be, let's see, this here is r is equal to 1 minus cosine of theta. And this other one here is r is equal to 1. So I'm trying to find this region right in here, which means the area that's inside of r is equal to 1, but it's outside of the cardioid 1 minus cosine theta. Now, I want you to notice that there are two intersections. We have one intersection here and one intersection here. We must go through and we must find those intersections. All right, so let's go through and let's take some time to see how we're going to find those intersections. So I have here r is equal to 1, and I also have, let's do it with this one here, and I also have r is equal to 1 minus cosine of theta. So what I'm going to do in order to find those intersections is I'm going to equal them to one another. So I'm going to say these two must be equal to one another if they're going to be intersecting, which means we're going to get 1 is equal to 1 minus cosine of theta. Subtracting the 1 over and dividing by a negative, we get cosine of theta must be 0. Well, where does cosine of theta, or where is cosine of theta equal to 0? So we now have to find those values. So cosine of theta is equal to 0. That happens when theta is equal to pi halves, and then it goes again at every pi halves increment, which means we're going to keep adding every pi increment. We're going to be adding pi k every single time in order to find those intersections. So for k being an integer. And that's k being an integer. Now, I got to find these two intersections. Well, naturally, the first one that I see right up here, one of them, the intersection, one of them, we get to see its pi halves. But again, the way we're integrating with polar coordinates means that when we set up our integral bounds must be increasing from the bottom towards the top. So if I go from pi halves, just like this, and if I try to find this one down here, and let's say I mistakenly do 3 pi halves, well, 3 pi halves would be traversing in this direction, which, again, that direction, this area is not reflected in that direction, which means we cannot use 3 pi halves, because then, whoa, ¿qué pasó? because then that would mean that our lower limit of integration would be pi halves, which would be incorrect at this point in time. So what we then want to observe is we then want this angle measurement, but we need a coterminal angle with it. So if we want it to be increasing, how about we then go for our k values? Well, if k was 0, k being 0 got us, and I'm going to write this, k being 0 got us that we got pi halves. Well, what if we try k is equal to, let's say, -1? If k is -1, that gets us a different theta value, -1, so it's going to be pi halves minus pi. That's going to be negative pi halves. Now, will that be increasing in the positive direction? So will that now be increasing in this direction? Yes, it will. It will be increasing in this direction for both of these graphs, which means we are on the right track now. All right, so we found our values that we need. We need theta is equal to pi halves, and we also need theta is equal to negative pi halves. So to write this specific integral, I'm going to go through and I'm going to say I need to find the area here, and this area is going to be bounded by these bounds, negative pi halves to pi halves, there we go. All right, and I'm going to do the outer function minus the inner function. So radii 2 minus radii 1, or radii 1 minus radii 2, however you want to see it. But again, it's the outer radii minus the inner radii. So the outer radii, that's going to be 1, so we're going to do 1 squared. So it's going to be 1 squared. Sorry, I'm going to insert a half over here because the formula uses 1/2, so that's going to be 1 minus the function that is the innermost function here, which is 1 minus cosine theta. And that's squared, and that's d theta. Now I'm going to elaborate here a little bit more. This here was radii is equal to 1, and this here was the radius is equal to 1 minus cosine of theta. And this was the outer radii, or outer radius, minus the inner radius. And again, this goes back to how we started defining these functions right in here, and saying that if we wanted to calculate the difference between these two functions, then we just take the outer minus the inner, right? And that area, again, is just 1/2 because the area always uses that 1/2 value. So now that we have this set up, we can then go through and we can finish our calculations. So let's go through and let's simplify this integral just a little bit more. This is 1/2 multiplied by the integral from negative pi halves to pi halves. There we are. All right, and now this is going to be, let's see, I have 1 minus, let's expand all of this. That's going to be 1 minus 2 cosine of theta plus cosine squared theta d theta. Looking good. All right, let's keep going. The ones are going to cancel, so that's not too bad. All right, again, I still have the half there, so I'm going to keep the half out there. Negative pi halves to pi halves, the ones cancel and the negative distributes. So we have 2 cosine of theta, because the negative is distributing, minus cosine squared theta, and this is d theta. Perfect. Now, one of the items that I want you to observe here as well is that we have symmetry occurring. There is symmetry occurring here. Both of these graphs are symmetric along this x-axis, or as we like to call the polar axis. So, if we wanted to, we can just double the area going from theta is equal to 0 over to theta is equal to pi halves. So what does that now look like? Well, I'm going to double this area, which was the area that I was going to find to be this 1/2 times the integral from 0 to pi halves for the same integrand, 2 cosine theta minus cosine squared theta, and that's d theta. Now notice the reason I wanted to do this is because now the 2 and the half kind of cancel out, which means all we're left with in order to do this evaluation is we need to solve the integral from 0 to pi halves for 2 cosine of theta minus cosine squared theta d theta. That's awesome. So again, I'm doing the 2 and I'm doing the bounds. I'm using this using symmetry along the polar axis. Awesome. So that's the reason why I multiplied by 2 and then I restructured the bounds of integration. Now again, once we look at that cosine squared, we then go back into our training and saying, okay, well, I see a cosine squared there, which means I'm gonna naturally need to use a power reduction here. So this is now gonna look like 2 cosine of theta minus, and this is, and this is now going to be 1/2 multiplied by 1 plus cosine of 2 theta, and this is going to be d theta. All right, so what I want you to do is I want you to keep going from here. Now that we use a power reduction, now that we set all this up, let's go through and let's figure out if we can go ahead and solve this. So I want you to go ahead and solve it. So put pause on the video, take some time and arrive at a conclusion for yourself. All right, and again, I'm really hoping that you're taking the time, putting pause on these videos and working these out. They're going to be highly beneficial for you, especially if you're in a STEM major, to make sure that you know how to evaluate these integrals. All right, so the evaluation here should be 2 minus pi fourths. Awesome. All right, so looking good so far. Now, what we're going to do is we're now going to be talking about a specific value or a specific formula to find if we can extract the length of a curve in polar coordinates. All right, so what I want to then extract is going to be a recall, and I want you to recall the arc length. The arc length formula that we were using just a few sections ago was the arc length formula. We went from some alpha to some beta, and this was, let's say, dx dt squared plus dy dt squared, and that was the square root of this, and that was going to be with respect to t. So this was an arc length formula when we were doing a parametrization. Now, what we're going to be in the business of doing here is we're going to be now looking at the equation that we're going to be using for the length of a polar curve. So I'm going to go through and I'm going to write that formula here, that we're going to have the length of a polar curve being given by the integral from alpha to beta for r squared plus dr d theta squared, and that's going to be d theta. All right, so for this arc length we then need to figure out, okay, well, what is going to be the angles that we're traversing in order to find this starting and this stopping point for this curve. Once we find that segment, we're then going to be able to say, okay, well, now that we have this segment, we know the parametrization, because the parametrization is going to be given in terms of theta. So we can go through and we can find everything that we need. All right, so let's go through this example here. So here goes this example. We want to find the length of the cardioid, which is going to be r is equal to 1 minus cosine of theta. Alright, so r is equal to 1 minus cosine of theta. And again, if you want to look at a visual for this cardioid, by all means go ahead and graph the cardioid. Alright, I believe we've already graphed this cardioid in one of our previous examples. Right, so that previous example was right up here. That 1 minus cosine theta was given by this pink cardioid right in here. So that's the length of the curve that we're going to be trying to find. So as we start looking at this, we're going to say, okay, well, there's a few things that we have given to us, right? One of the first things that I want to extract here is that we're given my radii, or radius here, in terms of my function. So this in here is my function of theta. All right, nice. Now let's see if we can find the derivative of this specific function. So we're going to find the derivative with respect to theta for r, and that's going to be d theta for 1 minus cosine of theta. All right, that's going to mean that my derivative here, dr d theta, is going to be just sine of theta as such. All right, now I'm going to work on my integrand really quickly. So let's work on that integrand really quickly. So my integrand here is r squared plus dr d theta squared. So r is this piece here, so that's 1 minus cosine of theta. I'm going to square that, plus my derivative squared, which is sine of theta squared. Let's go through and let's expand all this. So 1 minus 2 cosine theta plus cosine squared theta plus sine squared theta. And now you're going to see here that as we do this, these first two pieces here, that's your Pythagorean identity. So this is your Pythagorean identity. Which means it's equal to 1. So what we really have left is just this 1 minus 2 cosine of theta. Alright, not too bad, not too bad. So now that we have this, let's go through and let's insert it into our integrand and see what we can do here. Alright, so I'm going to start finding this arc length, L. The arc length for the whole cardioid. Now the whole cardioid, we're going to be going from 0 to 2 pi. That's to make sure that we get the whole length, because again the period is not adjusted here, so it remains from 0 to 2 pi. Alright, and now I'm going to take the square root of the value that I just found, this 1 minus, my apologies, it's not 1 minus, cheese and crackers. This is actually 2 minus, because again that was a 1. For some reason in my mind I was canceling it out. I have no idea why. So this is 2 minus 2 cosine of theta, and this is all inside of the square root, and this is going to be with respect to theta. Alright, it's looking pretty good so far. Now let's see what we can do at this point in time. Alright, so let's look at that integrand, or more specifically, let's look at that radicand. Alright, so I'm going to highlight the radicand here, and let's highlight the radicand in this particular color. We'll go with pink. Alright, so that's my radicand. So I'm going to be working with that radicand on the side, that way we can see what's taking place here. So with that radicand, 2 minus 2 cosine theta, so that kind of reminds me of this, 1 minus cosine of theta. Alright, this kind of reminds me of something special here. Now, the thing that it kind of reminds me of is that I have a 1 minus cosine theta. Notice here, I can't exactly simplify anything besides factoring out that 2. But what I do know is I know one of these, let's say, double angles is sine squared theta. Now, I'm going to use this to my advantage because this kind of looks like that, just in a slight change, in a slight version of it. Alright, so what I'm going to do here is I'm going to multiply by 2 on this side, so it's going to be 1 minus cosine of 2 theta, and this is going to be equal to 2 times sine squared theta. Now, their issue here on the equation that I'm looking for the radicand is that it's cosine of theta, but the equation that I'm working with over here in red, this identity has 2 theta for that cosine in its argument. But theta here doesn't have the 2, right? Because it was that power reduction, or that, one of those power reduction formulas built off of a double angle for cosine. Which means, let's go ahead and let's apply the half angle here. Well, if I take the inner angle, and if I divide by 2, wouldn't this naturally then become 1 minus cosine? Remember, I'm going to divide by 2. So divide this by 2, theta is equal to 2 sine squared, and remember I'm dividing the angles by 2, which means shouldn't this be the same? Or if you want to say, okay, well, Mr. Castor, you're using theta very, very loosely here. Alright, so let's say this was a different angle measurement that I want to interpret here. So let's say it was just x. So x, if I divide this by 2, then that's going to give me 2 theta, and if I divide this by 2, then that's just going to give me x over 2. So naturally, this 1 minus cosine just turns into this double angle here, or this half angle formula that I'm looking at. So this now just turns into 2 times, and that's going to be this piece right in here, 2 sine squared, and I'm going to keep using that theta squared, or sorry, theta divided by 2. Now that turns out to be awesome, because using that substitution, then I'm now going to be able to say, well, that's just 4 multiplied by sine squared theta over 2 d theta. And that was because of this piece here. So once I was able to do that, I resubstitute. Nice. So now I can just go ahead and I can figure out what the square root of this is. Alright, let's keep going. So let's figure out what the square root of this is. This is going to be 0 to 2 pi, and this is going to be 2 times the absolute value of sine of theta over 2 d theta. And again, whenever we work with a square root, I want you to always recall that anytime that you're working with the square root of some variable squared, this is going to be the absolute value of x. Alright, it's never just x by itself, it's always the absolute value of x. We then must interpret, will it always be positive? Now, if we take the angle from 0 to 2 pi, we cut that interval in half, that's just going to give us the angle from 0 to pi. So is sine on the interval from 0 to pi always positive? And the answer is going to be yes, it's always going to be positive. In that sense, we can always, or in this particular case, we can just drop the absolute value, because on the interval, sine is always going to be positive. There we are. Looking good. All we need to do is integrate this. This should be a pretty nice integral. If we integrate this, alright, the integral of sine is going to be negative cosine, alright, but we're dividing by 2, so we got to counteract it, so that's going to be negative 4 cosine of theta over 2. And again, you can take the derivative here. Taking the derivative of negative cosine should be positive sine, and then the derivative of the inside is going to be 1/2. 1/2 is going to multiply 4, that's going to be 2, which means we're good. Evaluate this from 0 to 2 pi. Let's see what we get. We should get just 8. So the arc length of this cardioid is 8 units. Interesting. Awesome. So I hope you all enjoyed this lesson for arc length. For arc length and areas in polar coordinates. All right. So I hope I will see you all next time.